is Parneet Singh, and in this part of the project, I'll be presenting my results for Part D and Part E, which include determining the maximum velocity and its location, as well as calculating the pressure gradient using both fluent results and theoretical analysis. So for Part D, we're going to go to the velocity graph right here. I already have it on the document. I determined the maximum velocity and the height at which it occurs using my fluent velocity profile. Um, what's it called? From the profile, I identified the highest point on the curve, which corresponds to the maximum velocity in the flow. The maximum velocity is approximately 7.43 meters per second and occurs at a height of about 1.75 times 10 to the negative 3 meters from the bottom plate. One important thing is that the maximum velocity does not occur at the center of the channel, which would normally be expected for pure Poisson flow. Instead, the velocity profile is skewed upwards towards the top plate. This happens because the flow is a combination of Poisson and Couette flow. The top flow is moving in the positive direction at 3 meters per second, while the bottom plate is moving in the negative direction at 2 meters per second. Because of this difference in wall motion, the fluid is dragged more strongly in the direction of the top plate, which shifts the velocity profile upwards and causes the maximum velocity to occur above the center line. This confirms that the velocity distribution is asymmetric due to the combined effects of pressure-driven flow and moving boundaries. Now I'm going to transition to Part E, where we determined the pressure gradient using both fluent results and theoretical analysis. And first, I'm going to go to the pressure contours right here. From the fluent pressure contour, observe that the pressure is highest at the inlet and decreases towards the outlet. The inlet pressure is approximately 60 pascals and the outlet pressure is approximately 0 pascals, indicating a pressure drop of about 60 pascals along the channel. The channel height is 0.01 meters, and since the length is defined as 150 times the height, the total channel length is 1.5 meters. Using the definition of pressure gradient as change in pressure over length, I calculated that the outlet minus inlet divided by length, which gives us 0 minus 60 divided by 0.5, and which was negative 40 pascals per meter, which is the pressure gradient. The negative sign indicates that pressure decreases in the direction of flow, which is expected for internal flow. Now I'm going to go down to the theoretical calculations right here. I'm going to zoom in. Okay. Yeah, so I determined the pressure gradient theoretically using the relation for combined Poisson and Couette flow. The average velocity is related to the pressure gradient by dp over dx equals negative 12 mu over h squared times the quantity of average velocity minus the average of the wall velocities. Substituting the known values, the top plate velocity is 3 meters per second, the bottom plate velocity is negative 2 meters per second, so their average is 0.5 meters per second. The viscosity is 0.001 pascal seconds, and the channel height is 0.01 meters. When I simplify the constants, the equation becomes negative 120 times the quantity of average velocity minus 0.5. So with the final substitution, I got negative 120 times 0.833 minus 0.5, which is 0.333 right here. And that gave me the answer of negative 40 pascals per meter. This matches the value obtained from fluent, confirming that the theoretical analysis agrees with the simulation. Overall, the agreement between the theoretical and fluent results confirms that the flow is fully developed and the simulation accurately represents combined Poisson-Couette flow behavior. And yeah, this was Part D and E for our project. This is the Part A, velocity contours. Part B, the pressure contours. Part C, the velocity profiles. the part D, maximum height and maximum velocity and height, and then part E, which is the calculations. Um, this was project 3, fluent 2D flow simulation of combined Poisson plus co-op flow. Um, I did this with my partner Paul Norris, who did the simulation on Fluent already. And yeah, I think that should be it. Thank you so much.